The advent of vacuum tubes enabled the massive growth of the electronics field in the early 20th century. As old as this technology is, however, it's relatively new to me. In this video, I'll attempt to power up and test the basic parameters of the 6V4 or EZ80 double diode tube, and then evaluate a basic prototyping setup designed for use with vacuum tubes. My test specimen is one I've had from my early teens, removed from an old Australian-made AWA radio, which was destined for the scrap heap. The markings were painted onto the tube, but most have rubbed off. However, there is a production or date code that looks like 427, and the remnants of the final part of the word mini-watt logo and the word Australia are still visible. As I've already mentioned, the 6V4 is a double diode tube. Like modern semiconductor diodes, the vacuum tube has an anode and a cathode. In fact, this tube has two anodes, which provides full wave rectification of a center-tapped transformer. Using the semiconductor symbol for a diode, the two diodes can be visualized like this. Since the vacuum tube relies on the emission of electrons from the cathode, heat is applied to the cathode via a heater element, so provided a suitable voltage potential exists between the anodes and cathode, the electrons can escape the negatively charged cathode and flow to the anodes. Remember, we are talking electron flow here. Usually we regard current flowing from positive to negative, the so-called conventional flow. The test setup is quite simple and has four main elements. First, the vacuum tube itself. Second, a 6.3 volt DC supply, which is attached to the heater element, and that supplies 600 milliamps of current. Third, an ammeter is placed in series with the cathode to measure current flow through the tube. And finally, a variable DC supply to place a potential between the anode and cathode. The physical setup is straightforward enough, but as you can see, it is a bit of a mess. Another point worth mentioning is the temperature of the tube itself. It gets hot, and it can easily melt any plastic surface on which it might be resting. To thermally insulate the tube, I placed it on a piece of fiberglass PCB board. This setup is kind of clumsy, so I decided to make a system that would meet two basic criteria. First, it would allow the vacuum tube to be free of any physical contact with a surface. Second, it can provide a secure but solderless method of connecting components to the tube to test different circuit configurations. To meet the first criterion, an aluminium plate would act as a chassis on which a valve socket would be mounted. This is a standard arrangement for vacuum tubes in all sorts of appliances. To fulfill the second criterion, I decided to use terminal strips to provide solderless connections. Given the high voltages and currents used in vacuum tube circuits, and the safety and operational consequences of having components making poor or intermittent contact, I figured that mains voltage rated, so 240 volts AC, terminal strips would be suitable. Although the aluminium plate should ideally be mounted horizontally, mounting it in this over-vertical arrangement keeps the center of gravity of the setup squarely over the base, preventing tipping. It also provides easy access to the terminals and wiring for making measurements. As an additional failsafe feature, I've added back-to-back Zener diodes across the heater supply to provide some short-term clamping protection in the event I accidentally apply too much voltage. I first learned of this idea from the YouTube channel Shango066, a channel definitely worth looking at if you're interested in repairing solid-state and vacuum tube electronics. Anyway, I couldn't remember the exact wiring arrangement Shango066 used, so any mistakes shown here are mine and mine alone. One important point to remember with using the values here is that it's strictly for a 6.3 volt DC power supply. If you were to use a 6.3 volt AC power supply, say from a transformer tap, the peak voltage would actually be 8.9 volts, which would cause the Zener diodes to clamp the waveform to 6.88 volts. This would result in insufficient power being delivered to the heater element, affecting performance. With the valve fitted to the prototyping chassis, it's time to power up to test its performance. The valve takes about 18 seconds to reach full heat, which is being demonstrated here. Even though this is an obsolete technology, I find these devices absolutely mesmerizing. The mirrored glass from the getter, the glow of the element, they give the feeling of being mildly impossible devices, created in a world we never experienced and that has long left us. The test results. This chart is from the EZ80 tube datasheet, and this tube is functionally equivalent to the 6V4. By increasing the anode voltage and plotting the current flow for each anode, we end up with these results. I limited the flow to 50 mA for both anodes, since I was applying straight DC current and not an AC waveform, for which this tube is designed, and also because I didn't really want to push my luck. This is an old tube and I don't really know what I'm doing. The current through each anode roughly tracks with the datasheet graph. At 50 mA of anode current, the difference in anode voltage between the anodes was about 3 volts. I don't know if this degree of difference is a typical example of production variation or the result of performance degradation due to usage. I imagine that this tube was used with a center tap transformer, so the power load across each anode would have been fairly symmetrical. Anyway, if you have any thoughts on this, please let me know in the comments below. So I'll wrap it up here. I'll try using this setup to prototype an amplifier in the near future. If you can spot any obvious problem with this setup, I'd welcome your feedback in the comments. Thanks for watching and have a terrific day.